Okay, we are going to look at a couple of practice problems related to Module 7. I have uploaded the practice problems on Module 7 folder. If you go to Blackboard, click on Module 7. You see a folder for practice problems. Click on that folder, and then you see the list of the questions. Okay, open the questions. So I'm going to go through these questions one by one and solve them for you. So in the first question, it says, a manufacturer is interested in the output voltage of a power supply used in a PC. Output voltage is assumed to be normally distributed with a standard deviation of 0.15 volt, and the manufacturer wishes to test the null hypothesis of average being equal to 5 volts against the alternative hypothesis that average is not equal to 5 volts. So our random variable here is voltage of the power supply in a PC, and the voltage, as we can see in the problem, has been set to have normal distribution with average mu that we don't know, and the standard deviation of 0.15 volt. And our null hypothesis is that the average voltage of these PCs is 5 volt, and our alternative hypothesis is that the average is not equal to 5 volts. And we want to find the critical region for this test, where we know that alpha, our significance level, is 0.01. Since this is a two-sided test, if I draw the shape of the normal standard distribution, this is going to be this shaded area. And to find the border of this shaded area, I need to find z of alpha over 2 and minus z of alpha over 2. And alpha here is 0.01. So alpha over 2 is 0.005. So I have to find z of 0.005. And to be able to do that, we are going to go to the z table. And here I have to find 0.005. So both these numbers are close, so it doesn't matter. So I'm going to pick this one, and this number corresponds to minus 0.258. So the result is 2.58. So that's going to 2.58. So then the critical region is going to be any place where the value of z statistics is less than minus 2.58 or greater than 2.58. So that would be our critical region. And obviously our acceptance region is going to be any value of z that is between minus 2.58 and 2.58. Let's go to the second question. In the second question, we have that we have a hypothesis to test a population mean to be equal to 10 against the alternative hypothesis that the population mean is more than 10. So the null hypothesis is that the population mean is 10, and our alternative hypothesis is that population mean is more than 10. We know the variance of the population is sigma, and what is the critical value for the test statistics for the following significance levels. So if alpha equals to 0.01, what is the critical value? So since here we have a one-sided test, if I want to draw the diagram related to normal standard, this is going to be the critical region. The shaded area is going to be the critical region, and this is going to be the z of alpha, and this area is the one that is basically alpha. And so in this scenario, it's going to be z of 0.01. And again, if I look at the table, 0.01 is, so this is the right value, and this value corresponds to 2.32. So let's go back. So z of 0.01 is 2.32. And that's going to be the critical value, and the critical region is going to be any value greater than 2.32. So if I get any test statistics that is greater than 2.32, that falls in the critical region, and the specific value of 2.32 itself is critical value. If I wanted to calculate the critical region for this test, for example, if mu equals to 10, but a null alternative hypothesis is mu less than 10, then and alpha was still the same number, 0.01, then the critical, for to calculating the critical region, if I draw the graph of the z normal standard, so this is going to be basically the critical region. So this area will be alpha, and this is going to be minus z alpha. And then the critical region will be any value for the test statistics that is less than minus z alpha, and that's going to be any value for z that is less than minus 2.32. This is going to be our critical region. And for the critical value, that's going to be this value itself, and that's going to be minus 2.32. Okay, let's go to the third problem. So in this problem, we are looking at a manufacturer, and we are looking at the output voltage of the power supply in a PC. The distribution of the voltage of this power supply is assumed to be normal and with a standard deviation of 0.25 volt. So the voltage is our random variable and is assumed to have a normal distribution with an average that we don't know and standard deviation of 0.25 volt. And we wish to test the hypothesis that average is 4 volt against the alternative hypothesis that average is not 4 volt. And we are going to take a sample of size 8, so that's our sample size, and we want to calculate the p-value corresponding to this test. So obviously here we have a two-sided test, and the formula for the p-value for a two-sided test is 2 multiplied by probability that the z random variable is greater than the absolute value of the test statistics, whatever it is going to be. So here in part A, the value of the test statistics that has been calculated after taking a sample of size of size 8 has been recorded to be 4.1. Now I have to calculate the test statistics corresponding to this value. So the test statistics is going to be x bar minus mu divided by sigma over square root of n. That's going to be 4.1 minus 4 divided by 0.25 divided by square root of 8. And this is going to be 1.13. So p-value is going to be 2 times probability that the normal standard random variable is greater than 1.113. That's going to be 2 multiplied by 1 minus probability that z is less than 1.13. And to calculate this probability, we are going to go to the z table. That's going to be here, 1.13. So the probability of z less than this number is going to be 0.87. And when we do get the calculations, it's going to be 0.258. So this is our p-value. And if, for example, I was going to run this test under the significance level alpha equals to 0.1 on significance level of 10%, if that was alpha, and this was the corresponding p-value for this test, what would be the result of, what would be your conclusion? Would you reject the null hypothesis or would you fail to reject the null hypothesis? As we can see here, p-value is greater than alpha. And as a result, our test statistics is in the acceptance region. So in this scenario, we for sure fail to reject the null hypothesis. For part B, we are expected to calculate the p-value if x bar, after taking a sample of size 8, the value of x bar has been observed to be 3.8. And in this scenario, again, I'm going to calculate the value of the test statistics. That's going to be x bar minus mu divided by sigma over square root of n. X bar here is 3.8 minus 4 divided by 0.25 divided by square root of 8. and that's going to be minus 2.26. So for the p-value, I have to calculate 2 times probability that z is greater than absolute value of minus 2.26. That's going to be 2 multiplied by 1 minus probability that z is less than 2.26. 2 multiplied by 1 minus, so probability of z less than 2.26. 2.26, that's going to be here. So the value of probability of z less than 2.26 is 0.988. And when we do the calculation, it's going to be something close to 0.023. So that's going to be our p-value. And again here, if alpha is 0.1, if the significance level is 10%, then here we can see that our p-value is definitely less than alpha. Then in that scenario, we are going to reject the null hypothesis. Even if alpha was 0.055%, if our significance level was 5%, we still would reject the test in this scenario as well because our p-value is very small. So in this scenario also we would reject the null hypothesis. And also if, let's say I'm going to consider parses. So let's say in this scenario, I'm going to look at the hypothesis, null hypothesis that mu equals to 4, but the alternative hypothesis is that mu is less than 4. I have taken a sample of size 8, and then the average of the sample has been observed to be 3.8. And let's say I want to calculate the p-value in this scenario. P-value is probability that z is less than the test statistic. So that's going to be the probability of z less than test statistics is x bar minus mu divided by sigma over square root of n. That's going to be probability of z less than 3.8 minus 4 divided by 0.25 divided by square root of 8. That's equal to probability of z less than minus 2.26. And to find this probability, we need to go again to the z table, minus 2.26. So let's go here and try to find the value of minus 2.26. So that's going to be this value here, minus 2.26. And that's 0.011. 0.011. So if alpha, the significance level is 5%, then in this scenario, p-value is less than alpha. So we are going to reject the null hypothesis. Okay, now let's look at question 4. In question 4, again, we are looking at the same problem context. Again, we are looking at the voltage of a PC. This voltage is assumed to have normal distribution with an average that we don't know and the standard deviation of 0.2 in this scenario. And the null hypothesis that we have is that average is equal to 4 volt, and the alternative hypothesis is that average is not equal to 4 volt. And we want to calculate the probability of a type 2 error, given the fact that the true mean is 4.05. So we want to calculate the type 2 error or beta. So here again, since we are looking at the two-sided hypothesis test, so this is the formula for calculating the beta or type 2 error, or probability of type 2 error. And here we need to calculate z of alpha over 2. So obviously alpha equals to 0.01. So alpha over 2 is 0.005. So z of alpha over 2 equals to, and we can go to the table, find 0.005. So this is the value that we have found before. So that's 2.58. So z of alpha over 2 is 2.58. And delta is the actual mu. Let's write it. minus the mu that we have seen in the null hypothesis. So I'm going to call this mu null. And that's going to be 4.05 minus 4.05. We know that the sample size n equals to 10 and sigma equals to 0.2. So we have everything to be able to calculate that probability. So beta equals to probability of minus 2.58 minus 0.05 square root of 10 divided by 0.2, and similar calculations on the other side. So this is going to be the probability of P being less than minus 3.33, less than 1.785. And this is going to be probability of Z less than 1.785 minus probability of Z less than minus 3.33. And from the Z table, the first probability is, so Z less than 1.78, 78 is here, that's 0.96 minus probability of Z less than 3, minus 3.33, minus 3.33 is going to be this number, almost 0.0004. So that's about the same, 96%. So that's going to be the probability of type 2 error. Now let's assume, now that we are here and we are working on beta, let's look at the problem in a different way. So let's assume our null hypothesis is that our mu equals to 4, and our alternative hypothesis is that mu is greater than 4. So now, again, we are taking a sample of size 10. Alpha, our significance level is 0.01. And we want to calculate the beta, or probability of type 2 error in this scenario. So if the alternative hypothesis is in this form, then the formula for beta, or probability of type 2 error, is going to be the probability of Z less than or equal to Z alpha minus delta square root of n over sigma. So we also, again, similar to the previous scenario, we assume that the actual mu is 4.05. So in this scenario, then Z of alpha, or Z of 0.01, again, going to the table, is going to be, that's the number we had calculated here. So that's going to be minus 0.232. So then Z of alpha is going to be 2.32. And then delta in this scenario is going to be the actual mu minus the one that we have in the null hypothesis. So that's going to be the same value that we had in previous scenario, 0.05. And so then beta is going to be probability of Z less than or equal to Z alpha, which is 2.32 minus 0.05 square root of n divided by 0.2, our sigma. So then Z is less than or equal to 1.53. And going back to the table, 1.53 is going to be this number here, 0.93 or 0.94. So 0.94 is the probability of type 2 error. And remember the formula for, and you may say, okay, this is a large number for a type 2 error. And remember that in type 2 error, we want to calculate the probability of failing to reject ethanol, given that ethanol is not correct, right? So here, the actual average is 4.05, and we want to see if the average equals to 4 or not. So as you can see, the value in our null hypothesis is very close to the actual value. So the fact that, so it makes sense for us to have the type 2 error to be actually a large number. However, as the difference between these two numbers increases, as the value that we are putting in our null hypothesis is getting further away from actual mu, we expect to have lower value for beta. For example, here, let's assume that the actual mu is 4.2. So if I calculate the probability of type 2 error, that's going to be probability of z less than or equal to 2.32. Delta here is 4 point delta. Here is going to be 4.2 minus 4 is going to be 0.2. Minus 0.2 square root of 10 divided by 0.2. And that's going to be probability of z less than or equal to 2.32 minus 3.16, and that's going to be probability of z less than or equal to minus 0.84. And if we go to the z table to find minus 0.84, it's here. So we see that the probability is 0.2. So here we see that then the type 2 error, or the probability of type 2 error, decreases and goes all the way from 0.9 to 0.2. And this makes sense because now the actual mu is 4.2. And if you remember, the mu that we have in our null hypothesis is 4. So since the actual mu is further away from the mu that we have in our null hypothesis, there's a smaller chance for us to make the error. So the chance of making type 2 error decreases and goes to 0.2. Let's go to problem number 5. In problem number 5, we have an engineer who is studying the tensile strength of a steel alloy, which is used in a golf club. And this strength is estimated to be to have normal distribution with sigma equals to 60 psi. So strength is the random variable that has normal distribution with average mu that we don't know and standard deviation of 60 psi. We take a random sample of size 12 and the average of this sample is 3450 psi. So part A asks, if the mean strength is 3500 psi, what is the smallest level of significance at which you would be willing to reject the null hypothesis? The smallest level of significance at which you would be willing to reject the null hypothesis is basically our p-value. So part A asks you guys to calculate the p-value. So here it says that if the mean strength is 3500, so we want the null hypothesis to have the null hypothesis as mu equals to 3500, and our alternative hypothesis for mu not to be equal to 3500. So given the fact that our alternative hypothesis is a two-sided test, then the formula for p-value is going to be 2 multiplied by probability of z greater than or equal to absolute value of test statistics, or z naught. So that's equals to 2 probability of z greater than or equal to absolute value of, so z, our test statistics is x bar, which is 3450 minus average, which is 3500, divided by sigma 60 over square root of n 12. That's going to be 2 times probability of z greater than 2.89. That equals to 2 times 1 minus probability of z less than 2.89. And this probability, we can find it from the table, 2.89. So that's this value here, 0.998. So that's 2.8, and this is the column related to 0.09. So that's the probability associated to associated with 2.89, that's 0.998. So 2 times 1 minus 0.998, and that's going to be 0.0039. So that's going to be our p-value, the smallest level of significance at which we are going to reject the null hypothesis. So let's look at part B. In part B, it says, what is the beta error or type 2 error if the true mean is 3470 and alpha is 0.01? Okay. So again, let's look at our null hypothesis. Our null hypothesis says mu is 3500. Our alternative hypothesis says mu is not equal to this value. Actual mu is 3470 and alpha significance level is 0.01. Okay, so we want to calculate beta type 2 error. So again, here we have a two-sided test. Okay, so this is the formulation for beta. And to be able to calculate beta, I need to know z of alpha over 2. So alpha is 0.01. So alpha over 2 is 0.005. So I have to calculate z of 0.005, which we calculated for one of the previous problems. That's going to be 2.58. Also, the value of delta equals to the the actual mu, which is 3470, minus mu null, which is 3500, and that's going to be minus 30. With that, beta is going to be probability of minus 2.58 minus 30 square root of 12 divided by 60 less than or equal to z. 2.58 minus 30 divided by 60. Thus, we can calculate beta as probability of z less than or equal to 4.312 minus probability of z less than or equal to minus 0.848. So probability of z less than 4.3 almost is 1 minus, and this probability also we can find it from the table, 848 minus 848, 0.2, and that's going to be 0.8. So that's going to be the probability of type 2 error. And then in part C, it says, suppose that you wanted to reject the null hypothesis with probability of at least 0.8 if mean strength equals to 3470. What sample size should we use? Okay, so again, our null hypothesis is still mu equals to 3500. Our alternative hypothesis, mu is not equal to 3500. It says that suppose that we wanted to reject the null hypothesis. So probability of rejecting null hypothesis if the actual mu is 3470. So if basically actual mu is 3470, or in other words, this means null hypothesis is not correct. What we have in the null hypothesis here is not correct. So we want this probability to be 0.8. So probability of rejecting H null, if H null is not correct, is basically what we define as the power of the test, right? And we said that the power of the test equals to 1 minus beta. So if we want, so basically 0.8 equals to 1 minus beta, and as a result, beta is going to be 0.2. I write down the formula for sample size. When we have a two-sided test, n is going to be z of alpha over 2 plus z of beta to the power of 2, sigma to the power of 2, delta to the power of 2. So here I need z of alpha over 2. That's going to be z of 0.005. Z of beta, that's going to be z of 0.2 to the power of 2. Sigma, which is 6c to the power of 2. And then delta to the power of 2, which is 3470 minus 3500 to the power of 2. The result is going to be 46.79 or 47 sample. So that's going to be our sample size to be able to get to the desired power for this test.